Hi.
Good morning. All right, so give everybody a minute or two to jump in. Anybody got any questions about anything so far?
The homework.
Well, not
The homework. Hold on now. What you mean the homework?
What do you mean? What do you mean the homework? Cody, you know we have homework, right?
Yeah, have you started? I need help. God.
You mean the homework for the city games?
Yes, chapter 21. Well, chapter
Whoa.
22, 23.
Stop saying all those
I
chapters.
already been started that.
So
y'all give me anxiety.
what-
Quit saying all that.
those kinds of questions, like I said, ask them in Discord so you can post a picture and maybe get help from other people, or I can comment on it, or you can jump in and chat with me about it. Because like I said, during office hours, I leave myself in the voice channel in case somebody wants to pop in and say, hey, Dr. Ian, I got a question. And in which case I jump over and start chatting.
Your office hours are what again?
What?
Your office hours are what, one more time?
They're on the
Syllabus.
yeah, they're not syllabus. Oh yeah, they are on the syllabus too. But I also posted the office hours document in Genzabar e-learning. But because I mean there's a bunch of them. But 12 to 1 Monday, Wednesday, Friday, 2 to 3 Monday, Wednesday, Friday, and then pretty much all day Tuesday and Thursday. So yeah, like I said, I just go around doing my everyday stuff, sitting in that channel, and if you need something, pop in, we can talk. Otherwise, you can always post text in there, and I'll get to it whenever I see it.
Cody?
Hmm?
Have you even started on the homework?
I started one or two of them, but I ain't get that far.
Might want to get on that.
Yeah.
Right. It's hard.
Did y'all start yours?
Yeah, but let's just say
Because I already started
I
mine
have
though.
math work written down, but Dr. Dean knows once I write it down, somewhere in the middle it always gets messed up. So
Hey, that's a start though. That's what we like to see.
Yeah, because I'm ready to get on the road. Because I'm ready to get on the road so I can finish this quick, fast, and in a hurry.
is it true that we're not going back next semester?
I don't know.
I don't know how long the virus going in.
I haven't been told anything about that. I haven't even been told anything officially about the summer yet.
Well, Georgia is clean, so
No, it's not. No.
yes, it is. Look at the map.
Some people are saying that like there's some miscommunication because people are saying that schools aren't going back for the entire year kind of thing. But by year, they don't mean calendar year, they mean academic year. So they mean schools aren't going back for the next month. Now, some states are talking about like a long, long time. I think Ohio was one that was talking about doing it for
Oh
like
my God, I got Destiny test me
August.
right now.
But as far as I know, nothing has yet been.
Destiny test me right now.
Yeah, nothing has been
Jeez.
So
said
is it
about.
true that the seniors are graduating over YouTube?
Do what?
The seniors are graduating over YouTube?
Is that what you're doing?
I'm not a senior yet, but I'm just saying I don't want to be graduating from home. I want to graduate and have a little
Right.
walk across the stage.
So.
I better not be graduating from home.
Right. Do the good old fashioned university stuff.
Yeah, university style.
Let's see.
So y'all gonna put y'all gonna make chairs, put the cap and gown on them, and put the digital tablet on the chair, and then hand the diploma, put it in the chair, and say congratulations. And keep it going.
You should submit that so that you guys can get like digitally walked up there and everything. Yeah, that's what the letter they sent out says, that that there is a online commencement deal they're doing. So that ought to be interesting.
Very.
All right. So okay, let's move along. So we have a chapter, we're in chapter 22, and we're talking about reflection and refraction. So reflection and refraction. We talked about reflection last time, where if you have a flat boundary and you have a light wave front coming in, it's going to strike, and we'll just do the single ray approximation right now. It's going to strike and bounce off. And the rules that govern how this bounce happens are very simple. You draw a line that goes out of the mirror surface. So we'll call that a mirror. What is the green dashed line that goes out from the surface called?
Normal.
The normal, yeah. So you have the norm, and you have the, what's this incoming one called?
Incident ray.
The incident ray. And what about the one going away?
Reflected.
Yeah. So the rule that governs this is the incident angle and the reflected angle are equal. And this makes sense to pretty good sense to most people because, well, when things bounce, you kind of assume that they would bounce with some kind of symmetry to them. It turns out that light has the most symmetry when it comes to this kind of thing. So just remember, incident and reflected have the same angle from the normal. So this is what happens when light bounces off. But sometimes it doesn't. Sometimes you have light will go through this boundary. So we won't call it a mirror anymore. And what is it called when light goes through the boundary and it's not reflected? What is it?
If it goes through, that means refracted.
Means it's refracted. So this is refraction. But as some people may have seen, refraction doesn't always happen, I guess, cleanly. It doesn't just go straight through. Usually there is a bend. And this bend, like we showed last time, is what makes prisms work. But the idea is something like this, where you have an angle of incidence still measured the same way, and then you have the angle of refraction.
Tell me about
Again, it's measured from the normal. This is kind of important.
Okay.
Tiffany, can you mute yourself, please? Because he's talking.
So the way this refraction works is based off of this fun little equation. This has to do with all waves, but the equation looks like this. Sine of theta I theta so sine of this angle divided by the sine of this angle is equal to the velocity of the incident ray, the velocity of the refracted ray. So this might bring up a question. Why does this happen? Because if light travels the same speed, so this is, we'll say, constant. If light travels the same speed everywhere, then velocity over here and the velocity over here should be the same. But they're not. Because And they can't be, because then the angles would have to be the same. So it would have to come in and go out at the same angle, which means it didn't get bent at all. So this tells us that the speed of light inside of a different material can actually change. So when I said the speed of light is constant, I meant in air, or really it's constant within a medium like water or glass or jello, whatever. It is constant within that thing. But it's not the same inside and outside in the air. This is what causes, God, man, this is what causes refraction to happen at all. It's the fact that when light goes across a boundary, let's say up here we have air and glass. The light travels at a different velocity in air and in glass. Exactly why is kind of beyond the scope of our thing, but just for now accept that it does. And it's not, for most materials, it's not like considerably different for us, like different noticeable for us, because light is still pretty fast. I mean, it might only change by, 20%, but we can't tell the difference between, 30 million miles an hour and 15 million miles an hour. We can't tell the difference between that. It's just instant for us. So how does the speed of light have any effect on the light itself? What does the speed have anything to do with turning or bending the light? This is something that was always very interesting to me when I was learning about it. So let's take a step back. So we've been drawing single arrows, but remember, light is actually a wave. So this is the wave front. So this would be like if you were a surfer, you're standing over here. When you look up and you see the big wall of wave, you're looking at the front of this. So when you do that, you see the wave front. But the wave is not just a single arrow, it's actually a bunch of them, all pointing in the direction of that wave front. Well, now let's see what happens when this wave encounters something. So the front of the wave has to be perpendicular, right? So these guys have to all be running the same direction. Now don't think of it for a second as light waves. Think of it as you and your friends, which I'm sure this is something that y'all do, running forward while locked arm to arm, okay? So this is a demonstration that's very easy to see in class, but this is how we're doing. So each arrow is actually a person running. So you guys are running down the street. And suddenly, you're going to come into some, we'll do a boundary of water. Okay, so if you both are running into the water and you go straight in, then you both just hit the water. But let's say you're going in at an angle. So you don't go in like that. Let's say you're going in like this. Has anyone ever run in water before or tried to?
Yeah.
What happens if you're running toward the water? What happens when you get to the water?
If you like you going to the beach though, if you want to the water, then the wave will come to you.
Okay, so we're not talking about water waves. Sorry, we're talking about just you and your friend.
It's harder to like run. Like your force is harder to run with the water.
It's harder to run. So even if you're putting all of your effort into it, you can't run as fast. Period. It's just not going to happen. This is ramped up considerably more if you're talking about like a giant mud puddle or quicksand or something. So if you both run into the water, then you both hit the water and you both slow down. But what happens when you go in at an angle? This guy, what does he do? He hits the water first, right? So as soon as he hits, he slows down. But if you're both locked arm to arm, and the guy that's in the water is going slower than the guy that's not in the water, what's going to happen?
Repeat that question again.
So you two are running hand in hand. You know, you're locked arms, whatever. Or
Okay.
maybe you're holding hands and you're running. Yeah. You're running toward the beach.
Yeah.
You hit the water.
Which is too hard to run in the water.
It's harder to run in the water.
Mm-hmm.
So what happens? The guy that's in the water goes slower. But the guy that's over here, he doesn't slow down. So what happens if you and the person next to you are running at different speeds?
The bottom part.
They'll break apart. They won't be together.
You can't break apart. It's not possible.
They have to run at the same time.
Same time?
I mean, in The Incredibles, Flash is fast enough to go straight over the water. But in this situation, I'm meaning is either one lighter than the other, or the bottom is not parallel, or...
So they can't, here are the rules, they can't let go of each other.
So the other one's on top of each other, they still can't let go of each other?
So they're not on top of each other, you're running next to each other.
Gonna be like behind, they'll be like one in front, one behind.
What do you mean one in front,
So
one
like,
behind?
they're still holding on to each other, but like one will be ahead of the other? I don't know.
It's weird, but so like think about these two. Maybe this is a good analogy. These two things are you, and like these two things are like this. So these guys are coming in. What happens when the blue one hits the water?
The second one is higher than the blue one. The black one is higher than the blue one, so it's going to take longer for the black one to hit the water.
So it's going to what?
I don't know how to explain it, but The blue one is closer to the water, therefore the black one takes longer to get to the water, even though they're holding hands.
The black one takes longer to get to the water.
Yeah.
You're right. But I'm saying what happens for the time in between when the blue one first hits the water and the black one hits the water a second, you know, it's not a second, but a moment or so later.
I don't know. I guess the question's confusing.
It is confusing, but and so that's okay. But it's kind of confusing because it's so obvious that you wouldn't expect anything to work like this. So I actually like this analogy. I usually do the two people analogy in class because it's fun to watch. But let's say, for a second, that this is the floor, and I drop this thing.
It's at a higher angle than the...
So this thing's going in like this. What's going to happen?
The black is at a higher angle than the blue. So the blue's going... what?
When the blue hits, it stops.
Yeah. So the black never touches.
But the black doesn't stop. So if the blue is stopped and the black isn't stopped, what happens?
It keeps rotating?
It turns until the black one hits the water too, in which case they continue on at the same speed. But this is what would happen if you two are running toward the water. The first person that hits the water is going to stop and yank the other person around. And that's what happens here, is the light goes in, and as soon as the blue hits, it slows down. So the light turns until the black also hits, and then it proceeds in a line. So if you were to map this with our lines, we'll have black line and blue line. So they are together right now. But when the blue one hits, the black one is going to keep going until it also hits. So if we continue this, and the analogy is not quite perfect because this is like an infinite number of little people holding hands. But when that hits, this one's going to turn until they are both in a line together. The point is, their overall direction is now different. So they were coming in like this, and then they left like that.
So that means they all refracted together.
Yeah, so that's how refraction works. It's sillily as simple as that the difference in speed creates this turning. You could think about it as a rotation if you want to. I would be kind of careful of that because nothing's really spinning, but the forward direction is turning from that way to that way. The opposite is true. What happens if you're in the water? So this is if you slow down, then you get bent toward the middle, toward the normal. But what happens the other way? if you are in the water and you are linked together, so
the blue would come up first before the black?
whichever one hits first. So if we are in the water and we go to land and we're running, I got new markers and I don't know how to deal with how good they write, so it's difficult. So if these two are coming in and we're going from water to land, you can run faster on land. So as soon as this guy gets out of the water, he's going to be going faster than this guy. But they have to stay together. So, I mean, there's a lot of vehicles that work like this, where you have one, like, if anyone's ever driven like a, I don't want to say a tank, but like a caterpillar or it's not a backhoe, an excavator. With the treads, the way they work is you have two handles. The right handle, if you push it forward, it makes the right tread go forward. If you push it backwards, it makes it go back. Same thing with the left. So the way you turn is you push one of them forward and the other one back. That makes the right side go faster than the left, or vice versa, which is what causes the turn. So if this side hits and starts going faster, it's going to turn around and they're going to go this way. So depending on the boundary, you get refraction that either makes it, again, this is all based on the normal, okay? So if you're going from water to land, or water to air, I guess, for light, it's slower in water, and then it's going to refract out when it gets to land. When you're talking about air to water, it goes the other way. It bends inward. So this is, and it's all based on this sine theta thing. So this creates a very interesting little property. What if we go, let's say, through some glass? Okay, so we start in water and we go through a pane of glass. So over here, we're in the water, and air. Actually, let's do it like this. If you are a person swimming, if a light ray comes out of your head and hits that glass straight on, what is it going to do? What happens to that green light ray?
Is it gonna break?
No, because it's going straight into the glass. How much refraction is there if it goes straight in? If you and your friend go straight into the water at the same time, how much bending is there?
None.
None. Zero. Come on, you got it. So yeah, it's going to go straight through. Now let's see what happens to a light ray that's coming from your feet. And we're talking about going to that point. So that say there's a person over here looking at you. Say it's a kid, I don't know. Well, this light ray is going to go here. And light is slowest in the water. So what's going to happen when you go from water to something that's a little bit faster than water? So the right side is going to hit first, meaning it's going to bend to the left. Maybe I'll draw it slightly different. So when it hits there, it's going to go through and bend to the left a little bit. And when it goes through again, let's make it bend a little less. Glass to air, it might bend a little bit more. So this is an effect that you see when you go to an aquarium. Has anyone ever been to an aquarium? Where you have a glass tank on the side and you can see both below the water and above the water?
Yes.
Yeah.
Have you ever noticed something funny about
The light bends.
the picture you see just below the water looks totally different than the one you see above the water.